All right, so I've been an electrician 15 something years, and I've always been trying to understand things quite deeply. And one of those things is earthing systems. There's lots of things people say about them, or things electricians believe about how they work and how important, like, for example, the earth electrode is, that I like to question. A year or so ago, an article came out where a senior electrical inspector was also questioning the value of the earth rod, so that kind of vindicated some of the things I'd thought. So I want to talk a bit about that and get really technical. So I don't know who's watching, electricians or the general public, but for those that don't know, an earthing system is how we protect against electric shock and short circuits. So anything that isn't supposed to be live, if it becomes live, we want circuit protection devices to operate. And that's what earthing systems do. They ensure that earthing systems operate. Another thing they do is they protect against potential rise. So volt differences that could occur between people and equipment. Earthing systems prevent those voltage differences from rising. It's not the same as protecting against a short circuit, because you could just draw the tiniest little bit of current through the earthing system, and that could reduce that potential difference. So New Zealand has what's called an MEN system. Overseas, I think it's called a TNCS system. I should probably have those letters right if I'm going to record a video. If it's wrong, I'll edit something in. Terra, neutral, connected, separate. So they are connected coming into the house, and then they separate in the distribution board and the main switchboard. We have an MEN link, and then around on all the final sub-circuits, there's separate earthing conductors and neutral wires. The reason for this system is, instead of running earth conductors all the way back to the transformers, we just run phase conductors and a neutral conductor to each house or to each installation, and it reduces the amount of wires. It was a really good system back in the day when we had metal pipes running between the houses, although I've been told that it caused corrosion on the pipes, because you're putting current down the pipes and the electron activity there causes rust. But that aside, what these pipes acted as was a really big MEN connection between the houses. MEN stands for main, earth, neutral, link. So in the switchboard, there's the main earth bar and the main neutral bar, and they're connected. And then when you have the earthing system attached to the pipes, and the pipes from one house attached to the pipes of other houses, that's like another MEN link. So if your house loses its neutral, which is the main fault path, that's how, when you have a short circuit, the current flows at a high enough rate to trip the circuit protection. If your neutral's lost, you still have the neighbor's neutral, and the current can travel down the pipes. In New Zealand, the regulations require short circuit protection to operate within 400 milliseconds, which I guess should be enough that if you're holding a metal device or touching a metal surface that becomes live from that fault, it's only live for 400 milliseconds, and that's not enough time for you to suffer damage. But we no longer have metal pipes running between houses like that. We haven't done for a long time. Now it's PVC pipes. So that benefit's gone. And I'm convinced that with the disappearance of this shared fault path between installations, the MEN system now doesn't make any sense. I'm sure not everyone agrees with me, but I've got my reasoning. Now, the other kind of system that comes up a lot in these discussions that I think is a better one is a TT system combined with whole installation RCD protection. So back in the day when the MEN system was devised, either RCDs didn't exist or they weren't affordable. But now that we've lost the metal pipes, we have RCDs, which offer a kind of protection that wasn't really possible 100 years ago, 50 years ago. So we already have RCDs in a lot of installations and a lot of circuits. Older houses might not have them, but all new work is required to have them. And they do a great job, but they don't protect you against a main neutral fault, or as they call it overseas, a PEN conductor fault. But a whole installation RCD with a TT earthing system would protect against this, because Terra is what the acronym means, is you have an earth electrode for your installation and no MEN link. So if your neutral system becomes live due to a fault, your earthing system doesn't become live. But if you get voltage or current flowing to earth, you'll have a whole installation RCD which will trip. And it could be rated at 500 milliamps or maybe 100 milliamps, depending on the installation size and however it's designed. And 500 milliamps isn't really enough to protect a person, but what it's doing is it's protecting against a fault. So if that fault occurs, it should trip because of the fault, not because of a person getting an electric shock. And then we have sub-circuit RCDs to protect against a person getting a shock. Now back on the MEN system, the earthing system, like I said, used to be the pipes running between the houses, which worked really well. Not only did you get a really serious connection to the earth mass, but you had that connection to the neighboring neutral conductors if your one was lost. But now, just putting a rod in the ground, the connection you get is really bad. It's not enough to trip a breaker. A really good earth rod might give you 10 ohms connection. A bad one might give you 100 ohms. Overseas, where they have TT systems, you're actually required to test the integrity of the earthing system. So you put an independent earthen nearby, and you need to get a reading of at least 80 or 100 ohms, depending on the jurisdiction. Which brings me to one of my big arguments against the value of the earth rod. So everything we put in for electrical safety, we can pretty much mathematically describe what it's doing, how it functions, and at what point of failure does it stop performing its required job. So we do earth fault loop impedance tests to make sure that under fault conditions, the breaker is going to trip fast enough. We test RCDs to make sure they're tripping quickly enough under certain test conditions, and so on. But we test the continuity. You got to get half an ohm continuity between the main earth electrode and the main earth bar back in the main switchboard. But for the earth rod, there's nothing. There's no test to make sure the earth rod is achieving a good conductive path with the earth mass, which to me says it's not really doing anything important. Because if you ask people, oh, the earth rod's a bit rusty, do we need to replace it? You'll get differing answers, but people will just basically say, oh, if it doesn't look good, yeah, replace it. It's like, okay, but at what point of failure does it stop performing its job? And there's no answer. And the reason for that is because it's not really doing a job, at least not the way you think. Recently, someone did give me one answer of what the earth electrode does, is protecting against surges. So if you have an 11,000 volt power line fall on your power line and your house gets blasted with 11,000 kVA, that earth rod, it doesn't matter about the high resistance, because 11,000 volts is such a high voltage. that the resistance doesn't matter. So sure, your electricals in your house are going to get pretty fried, but the earth rod will help do something to take that voltage away and to cause the high voltage fuses to trip a bit faster. And maybe it helps against lightning strikes too. But that's not something the electrical legislation talks about. If that's the job it's doing, it should at least be described that here's the real benefit you get from these. Now, I did do a lot of research into this and was wondering, well, why don't we just have floating systems? Like in a medical situation, you'll have a completely isolated system. Phase and neutral are fully isolated, which means if the patient comes in contact with either conductor, they do not get a shock, because neither one of those conductors will create a fault path through the body. But if both conductors come in contact with that person somehow, now there's serious risks that can result from that, serious harm. So what they have in those systems is monitoring. There is an earthing system, but it doesn't operate protective devices, because if someone's in the middle of a medical procedure and the power suddenly turns off to a device, the results from that could be catastrophic. So instead of turning the power off, if a fault happens, an alert is sent out so that the doctors and technicians can safely resolve the fault without a sudden power loss. Because it takes 2 faults under that condition for harm to occur, so an alert is enough. But you can't do that for a whole installation, because one reason is you could have your installation fully isolated and you could have one metal appliance somehow have a fault where the frame becomes live. And then you could have a different metal appliance have a different fault where the frame becomes live, but from a different conductor. And now those 2 appliances create a fault path. So if a person touches both of them, they could suffer a serious electric shock. So that's one reason why you can't have a completely isolated installation. Isolating one piece of equipment is not the same as isolating a whole installation. Another reason is because when you have a transformer, you have to earth the transformer, because otherwise you can get stray voltages building up where the potential difference between the transformer and earth becomes quite high, and then you get like discharges, and those discharges can damage equipment and be dangerous. So you have to earth the transformer. You don't have to earth an appliance that doesn't have the same kind of risk of building up voltages as a whole transformer does. But like that's why tradition, like old school way of personal protection is an isolation transformer. You've probably seen them, those big orange things, big heavy box, you plug it in. They used to be used on construction sites, but now we have RCDs. Nobody uses that anymore, both because RCDs are a lot safer than that, and also because those things are bulky and heavy and awkward. But they were considered to offer a decent amount of protection. So I always wondered, well, if isolated is safer, why is it not always safer? One reason is the risk of 2 different appliances with faults, 2 different conductors, creating a fault path. Another is, the transient voltages that you could get if you don't earth the device. The earth electrode doesn't actually need to have a very good connection of earth in order to keep the energy levels low, the potential buildup. But the need to earth the transformer doesn't explain any benefit that might come from the earth electrode at the installation. Sure, if the transformer earth fails, then those earth rods at the houses actually become pretty important, because you actually need that protection. But using, first of all, the legislation and the people who design the system, nobody talks about using installation earth electrodes as a kind of backup protection for cases where the transformer earth fails. It's just not discussed. And secondly, earthing systems for the transformers are well maintained. There's a system for testing them and making sure they're in good shape. And that's how it should be too. If you need to earth the transformer, just earth the transformer. Don't go around putting earth rods in people's houses, telling them it's for one reason, but actually it being there for backup in case the transformer earth fails. So that's not the case. So then we're left with, well, what is the earth rod actually doing? We talked about how under certain fault conditions, it just will not trip. You could have 20 amps flowing through your earth electrode because of a dead short, and that won't trip your 20 amp circuit breaker, won't trip your 63 amp HRC fuse. You need your main neutral conductor to work as a fault path. The whole MEN system only works if you have an intact main neutral coming into the installation. Without that, the protection's gone. So this is the one weakness of the MEN system. The electrical system in New Zealand is designed under a 2 faults philosophy. So the idea is for harm to occur, there must be 2 faults. So another thing where only 1 fault can cause harm is a transposed phase and neutral conductor. But I don't think of that in the same category, because if you transpose the phase and neutral, somebody made a mistake when they terminated the wires and somebody failed to test that. So the solution to that is for electricians to do their job properly, for linesmen to do their job properly, for electrical inspectors to do their job properly. Just test your work. And I mean, there are cases of phase neutral transposition. People get punished from it from time to time, but we solve that one by testing. It's a really easy thing to do. If you can't do that test, you shouldn't be an electrician. I mean, I guess mistakes happen, but that's why we have testing. You make a mistake, and then before you finish your work, you go around and you check. And there's lots of testing the legislations require, which maybe you can get away with not doing. But phase neutral transposition, the things that could create that are things you have to test. So back on, that was a bit of a side tangent. Yeah, the loss of the mains neutral is the one single fault that the MEN system doesn't protect against. Other things you need 2 faults, like for example, you need your circuit protection to fail and you need to have a fault to earth, but there's just no protection against it. So like I said before, the TT system with an RCD would protect against it. But yeah, finishing off the point about what does the earth electrode actually do? So how rusty is it before it fails? No one can tell you. I would argue that if you went around and pulled all the earth electrodes out of all the houses, as long as the transformer earths remained intact, you wouldn't have a problem. So there was an argument that the earth electrode does help RCDs trip, because if you lose your main neutral, no, not in that case. It's not one that I've really understood, because you could have a situation where the fault is running through an RCD. The voltage created by a loss of neutral, the current that's generated from that fault runs through the neutral in and then back out through the other side of the neutral and then builds up on the other side of that. So if you get a shock from that, the fault path is not creating an imbalance in the RCD, so you don't get protection against it. Oh, I've just missed my turn. So the earth electrode can't protect you against a loss of neutral fault, even with RCDs, because The way it works is to get voltage on your earthing system from a loss of neutral fault, you need to have loads connected. Those loads are connected either through an RCD or not. If they are connected through an RCD, the current path to build up that voltage runs through the phase conductor of the RCD, through the load of the appliance, and back out through the neutral again. And then you get the other end of it on the earth conductor. So if you touch it and get a shock, the current is flowing through the RCD without creating an imbalance, so it won't trip. If you had that whole installation RCD with a separated earthing system, it would flow through the RCD because the voltage that you'd be getting a shock from can't come through the RCD because your earthing system isn't connected to the neutral system. This is getting quite technical. So there is an idea that the high resistance that the earth electrode gets, say 100 ohms in a bad case, that's not enough to trigger overcurrent protection, but it is enough to trigger RCD protection. But this is where we could talk about another risk that the earth electrodes bring, which is that they create a fault current between a person back to the conductor, because you've now connected to the neutral back to the conductor the soil around your house. So if you're standing on wet ground and bare feet near the earth rod, you have a really good connection between you back to the transformer. And if you then touch a voltage source, you can get a really bad shock and it could be fatal. A lot of electricians usually get shocks from time to time throughout the course of their career. Shouldn't be, but it happens. But usually nothing happens because we're wearing boots, we're standing on an insulated ladder, we're not holding the other side of the metal cabinet. When we get the shock, you just get a little tingle. But if you're really well earthed and you come in contact with that same conductor, the results could be catastrophic. I know one story. I was working at one house and the lady told me, years ago an electrician died under this house. And it's that being outside crawling in the mud factor that makes the risk so much higher than if you're standing on an insulated ladder. So earthing the soil around the house does not make it safer for people. But the resistance is low enough that the RCD could trip. Because I did the math, I think 7,000 ohms is still enough to get 30 milliamps flowing at 230 volts. I might put the proper math. I'll link to an article I've got on this that has all the numbers if you want to have numbers, but you get the idea. It doesn't take much current to trip an RCD, so even a high resistance fault path will still cause it to trip. The benefit there comes if the fault happens in such a way that no one's touching it at the time, but it trips before anyone touches it, great. But if that fault path is through a person, the RCD is going to trip anyway if there's enough current to cause any harm. So you don't need to increase the amount of current that could flow through the person. That's not making things safer. So I think that's about all I've got to say on that. Hopefully you found that interesting or informative. Let us know what you think down in the comments. I'm sure I'll get people disagreeing with me. And I will catch you in the next one.